Do you know that in chemistry, everything should be perfect? 1 bar, 1 molar, 25 degree, very perfect. However, in our real life cell is actually very chaotic and different from that. So today we will learn about the difference between the standard state in chemistry and also the standard state in living cells. Okay, so first let's talk about what standard state in chemistry. In chemistry, the standard state refers to the pure and most stable physical form of a substance at a pressure of 1 bar and a specified temperature, usually 298 Kelvin or 25 degrees Celsius. For solution, the standard concentration is defined as 1 molar. These conditions are very useful because they provide a fixed reference point for thermodynamic calculations such as Gibbs free energy and equilibrium constant. However, when we move from chemistry to biology, especially inside a living cell, these standard conditions are no longer realistic. Living cells do not operate at classical standard state conditions. Inside cells, concentration of metabolites are usually much lower than 1 molar and can vary continuously. In addition, cellular pH is tightly regulated from pH 7, which is why hydrogen ion concentration usually fixed when performing biological thermodynamic calculation. Biochemical reactions also occur in a crowded and noisy environment. These are open systems that constantly exchange matter and energy with their surrounding, and many reactions are coupled to ATP hydrolysis. Because of this, cellular reactions are often far from equilibrium. I will explain the standard notation used for Gibbs free energy in biochemistry, focusing on the difference between delta G naught and delta G naught prime. In thermodynamics, delta G naught refers to the standard Gibbs free energy change under chemical standard conditions. These conditions assume a temperature of 298 Kelvin, a pressure of 1 bar, and a concentration of 1 molar for all solids, including protons. This means the proton concentration is 1 molar, which corresponds to the pH of 0. Although these conditions are suitable for chemical reactions, but they are not realistic for living cells. Therefore, in biochemistry, we use delta G naught prime, which represents the biological standard state. In this condition, the temperature and pressure remain the same, but the proton concentration is fixed at 10 to the power of -7, which corresponding to pH 7. This value closely reflects physiological conditions inside most cells. The prime symbol in delta G naught primes indicates that protons are kept constant and excluded from the equilibrium expression. This is important because many biochemical reactions involve protons, and fixing the pH avoids the unrealistic energy calculations. In summary, delta G naught prime is used in biological systems because it provides a more accurate representation of energy changes in living organisms. For this reason, delta G naught prime is widely used in the study of metabolism, ATP hydrolysis, and other biochemical pathways. Now that the biological standards and its notation have been clearly defined, the next part of the presentation will focus on the mathematical derivation that explains how this definition affects the Gibbs free energy equation.
Hello everyone. So my role is to derive the mathematical link between standard chemistry and biology. We start with a general reaction where Nu represents the stoichiometric coefficient, the number of protons involved in the reaction. In chemistry, the standard state assumes a proton concentration of 1 molar. In biology, we operate at pH 7 or 10 power of -7 molar. When we substitute this value into the Gibbs energy equation, we can use log loss to pull out the exponent. This gives us equation from the slide. This is the master formula. The biological Gibbs energy equals the chemical Gibbs energy plus the correction term depend heavily on temperature. At standard lab condition, 298 Kelvin, every proton adds about 40 kJ per mole to the energy calculation. However, at body temperature, which is 37 Celsius or 310 Kelvin, this actually increases to 41.5 kJ per mole. This distinction is vital for accurate human physiological calculation. It is important to note, if a reaction does not involve hydrogen ions, the correction term vanishes, and the chemical and biological standard states are identical. That's all.
Aha! You just have seen how the equation is derived, right? I know. It's a lot of symbols and math. But don't worry, I will show you how the easiest way to use the equation. Now, let's see the real world example. Look at ATP, our body's battery. In normal chemistry lab, its energy value is positive 10. In chemistry, positive means no energy release. If our body works like that, we have no power to move or to breathe. But we are biological system. We take our biological number. We take the positive 10, add our gas constant and temperature, multiply it by concentration of pH 7. When you do the math, what will happen? The positive 10 turns into negative 30, right? Because it's now negative, it becomes exogeny and spontaneous. This jump from positive to negative exactly how our cell unlock energy to power life. Math proof, biology follow its own rule.
You just know, right, the example of how to use the equation. So right now, I'm going to be telling you the analysis of Gibbs energy. Did you guys know that your body has a master analyst to decide that your body has enough energy to move? That analyst is Gibbs energy. Joseph Gibbs worked in abstract math to predict how energy flow in the universe. But there's a catch. Standard chemistry happens at pH 0, which will kill a human cell. Because our cell lives at pH 7, we use a special biological version of math, which is delta G not prime. Now I'm going to be explaining to you the interaction of the tug of war, where you have to think of protons, which is H plus, as an energy shifters. In your cells, the low concentration of protons actually pulls reactions forward. This shift adds roughly 40 kilojoule over mole of energy. Without this pull, your muscles wouldn't have the energy to contract. So, the analysts prove that our bodies don't just use energy, but they strategically pull it from the environment to keep us alive.
Hi, so with me here, you have reached the last part of the video. So in my part, I'll be talking about the application of the biological standard state. Biological system calculation needs to reflect the physiological condition. So, the biological standard state mainly apply in the biochemical thermodynamics, which the reaction mainly occur at pH 7. So to use this free Gibbs energy calculation, we fix the ion hydrogen concentration at 10 to the power of negative 7, so that the value we get will be more realistic for the inside living cells. So the reactions that use this free Gibbs calculation is ATP hydrolysis, Krebs cycle, and also glycolysis, and many more, but three of this is between among of them. I'll be talking about the ATP hydrolysis. From the equation of the ATP hydrolysis, we can see that the delta G naught prime is a negative 30.5 kJ per mole. So this value indicates that the reaction is spontaneous and releases energy, so that it will drive many cellular processes such as active transport, muscle construction, and also biosynthesis. So therefore, by using this biological standard state, we know that how the energy is produced and utilized for the reaction. Thank you.